Hello, this presentation is related to the design, testing, and use of luminaires for horticulture. But first, I will introduce some ideas about the influence of light in the development of plants. With the word horticulture lighting, we can find lots of products and projects on the internet. These type of products are in the market for decades, some years ago using lamps with different special spectral distributions. But currently, many new products are based in the use of LEDs. There is an important market behind these products, and it is a growing one, even in countries with many hours of sun. The main reason for the use of artificial light is the only source of light, or as additional light for a greenhouse, is the increase of the efficiency. We can modify the natural day length, use less fertilizers, control the timing of the production, and improve the uniformity of the products in terms of shape or size. The light is one of the inputs for a plant to develop. Of course, there are other very important factors as the composition of soil, temperature, humidity, etc. But today we will just focus on the influence of light as one of the important signals perceived by the plants. In the process of growing and development, these plants are influenced by the surrounding light. For instance, photosynthesis, the use of energy for biomass production, flowering, seed development, germination, and plant morphology. The different actions mentioned are dependent on the presence of light with different spectral distribution. In some cases, the key factor is the ratio between different spectral ranges. For instance, the relationship between the quantity of red and far red in the light. The spectral interval of interest is wider than the visible, including UV and far red irradiation. And as important as the spectral composition is the duration of the artificial light, actually the duration of the dark periods, and even the dynamics, the progressive increase or decrease of the duration of darkness produce effects in flowering and germination. But not only the spectral composition is important for a luminaire, we have to obtain some parameters to quantify the amount of radiation provided by the artificial light, and the luminaires will be used to produce uniform beds of light, so it is very important how the radiation is delivered from the product. So I will introduce these three important characteristics of the products: the spectral power distribution, some parameters obtained from the spectrum, and angular distribution of radiation. I already introduced the importance of the composition of light. What I want to remark here is that not only the spectra of chlorophyll is important to grow plants, especially if we want to control the timing for the whole cycle and not only gain biomass. So that we have one of the keys for the design of luminaires for horticulture. Depending on the effects we want to produce, we will need a different spectral composition, and this can be achieved using LED sources, better than with other technologies. Here we can see the spectrum of a short list of LEDs that could be useful to design luminaires for this application. Not complete, of course. It is useful to find a certain combination of 3 or 4 types of LEDs, including also white LEDs in the combinations. Directly from the spectral power distribution, a lot of parameters can be calculated to quantify the amount of radiation provided by the artificial light. These quantities are based on radiometric units or numbers of photons per wavelength. In this case, just remember that the lower of the wavelength of the radiation, the higher the energy of the photon. I will only highlight some parameters widely used in the description of horticultural luminaires. Talking about these products, we usually refer to PAR units, which means that we are considering radiation between 400 nanometers and 700 nanometers, with a flat weight of 1 along all the interval. Photosynthetic photon flux represents CO2 assimilation per mole of incident photons. It is equivalent to luminaire lumens. Photosynthetic photons flux density is similar to photosynthetic illuminance measured in lux. Like illuminance, the average ppfd is often used as a target light level criterion for growing crops. ppfd and duration of exposure are used to calculate the daily light integral, DLA, micromoles per meter square second. Besides the information related to the spectral distribution, there are other important properties of these luminaires as the 3D distribution of the radiation. There are 2 low-key components for this distribution: the source itself of the lens and the lenses or reflectors used. Both generate the pattern of radiation. Some lamps can be used for these applications, but currently many products include LEDs as sources. Different multi-wavelength LEDs or combinations of LEDs can be used. Depending on the expected use of the luminaire, the radiation pattern needed is different. We may want to light big areas from a certain distance or work in near-field radiation. We can obtain different angular distribution of the radiation having the same LEDs as sources, just using different lenses. And these different angular distributions provide different radiation patterns over a surface. This is an example. Here we have two types of LEDs, 6 blue and 6 red. And this is their joint spectral distribution, similar to the chlorophyll B. Having only this group of LEDs, the ray tracing process for the simulation is easy. We only have to be sure that the model introduced in the software includes the real angular distribution of each type of source and the real spectral distribution. Then we perform the ray tracing process and we can see some results. As we didn't include lenses, there is no additional control in the direction of the rays. So we obtain as global angular distribution the same as the individual distribution of the LEDs. But this is not what we usually want, especially if we aim to radiate with high uniformity a big surface. Here you can see the value of PPSD, similar to irradiance, at different distances, and we see an important concentration of radiation on axis. Please note that the area covered in double at the right, and also the distance at the luminaire is bigger, but the pattern is similar. To increase the area irradiated and the uniformity of irradiance, we have to change the angular distribution of radiation. In this case, we have a Lambertian distribution, which varies similar values over a high range of angles. But we are interested in a non-uniform distribution, to have lower values in the front direction and much higher values at big angles, to facilitate a bigger amount of energy reaching longer distances. So we design a lens considering these requirements and perform again the simulation. We obtain a very different distribution, useful to irradiate big areas with a low number of luminaires distributed over the area. The radiation pattern is quite different. The spread of radiation and the uniformity is bigger. I talk about the design process. The same results that we can achieve with the simulation of a virtual product can be obtained with the measurement of a real product. After the design, the luminaires are manufactured and they should be characterized in the laboratory to obtain all the technical information required for the use of the product in different projects. The measurement of the spectral power distribution and the angular distribution of radiation will provide the information needed of the product, and then the next step can be done, which is the use of the luminaire in a real installation of the artificial light in a greenhouse. So we have to move to the final part of the presentation, lighting projects, or better say, radiation projects. We can use software for horticulture applications or use lighting simulation software, adapting the files corresponding to the luminaires to produce either photometric quantities, radiometric quantities, or PAR quantities, as we wish. These are the main steps in the process. We have to model of the installation, dimensions, geometry, calculation of the planes. Inclusion of relevant elements, especially those that could shadow the plants or those that will interrupt, reflect, or refract the rays. Selection of the luminaires, distribution of luminaires. Configuration of calculations, and perform the simulation. Here are 3 examples. First one, the greenhouse with pendant luminaires. Step 1 is the definition of the geometry and dimensions of a greenhouse. Step 2 is the definition of the elements that will shadow and reflect the light. Step 3 is the selection and distribution of the luminaires. It can be done manually or automatically according to certain criteria. And step 4 is the configuration of the process of calculation and running the simulation. The last step is the obtention of the output, the results of the simulation. If we achieve the expected results, perfect. If not, we should modify the distribution of luminaires, add or remove, or maybe mix different types of luminaires. The same processes can be seen in a different example. We can include vertical and horizontal calculation planes. We go through the same steps. An example for vertical forming. In this case, we have the calculation planes at different levels, but the whole process is the same. It is not so easy nor quick to prepare these projects, but the software has many useful tools to prepare very complete projects. And that's all. Here is my contact address. You can reach us anytime to discuss about design or testing of luminaires, also for projects, training, or consulting. Thank you very much.